This is VLSI data conversion circuits, lecture 54. In the last class we looked at the various trade-offs between the degrees of segmentation that are possible when realizing a DAC, and we said that all things being equal, it makes sense to have a decoding which is more segmented than one which is less segmented, okay. And we said the motivation for that was if the sigma NL remains the same and we can have a lower sigma DNL, you are obviously doing much better than you were doing with a solution which had a higher sigma DNL, right. Now let us look at another allied issue which is dynamic performance. Especially with regard to binary versus thermometer decoded DACs. So again let me go back to my simple example. Which was a 4-bit DAC example. So this is G, this is 2G, this is 4G, this is 8G, and this is controlled by B3, B2, B1, B0, Vref, RF, and V out. Okay. Now let us kind of see what happens when the digital code changes from 0 followed by all ones to 1 followed by all zeros, right. When the digital code was 0 followed by all ones, the output voltage, if I plot it as a function of time, would be 7 times G times Vref. Let us assume that this is the instant at which the code changes from 0 followed by all ones to 1 followed by all zeros. If all the elements are perfectly matched and B2, B1 and B0 turned off at precisely the same instant as B3 turned on, the output waveform would look like this, where this is 8G times Vref. On the other hand, if there is a small timing skew between the instants at which B3 turned on and B0, B1, B2 turned off, in other words, let us say B3 turns on before B2, B1, B0 turn off. Okay, so there is now certain instants, a certain period of time where all the switches are on. So assuming the op amp is infinitely fast and such, what do you think will happen to the output waveform? It will momentarily go to a very large value. In this particular case 15 G times Vref and come back to 8 G times Vref. Does it make sense? All right. Now consider what happens when the code changes from 2G to 3G. Any comments? When it is 2G, what will it, in other words, when the code goes from, this is a situation when 0 followed by all 1s to 1 followed by all 0s. I am interested in what happens to the waveform when I have 0 0 say 1 0 to 0 0 1 1. It should be 2G Vref here and 3G Vref okay. What happens when there is timing skew? Pardon, why? Let us say the only thing, I mean, if here if we assume that say the transition of this is delayed slightly, I mean only one current source is switching, one conductance is switching. So the transition will occur slightly delayed with respect to the current source, with respect to the when the code changes, all right. So can you comment on the two situations we have seen so far and what that means?
Second transition is like what will happen in thermometer?
Well, okay,
only one by one.
All right, but is there something more glaring that you notice?
Number of transitions.
Pardon?
Number of transitions.
No,
The error is used in, if you had taken the output at the beginning, or let's say integrate that, I will get an error.
no. One thing is that nothing is switching off, only current sources are getting more and more added.
Correct.
Whereas in the previous case, 3 of them are switching off and 1 of them is turning on.
That's correct.
If there is a time, if there is a time delta t difference between how fast you can turn on and how fast you can turn off,
Correct.
then you will see the kind of spikes you saw.
Yes, that's correct. But
Whereas even if there is such kind of timing skew in the second case, you will not see any kind of spike like that.
okay, so basically one thing that's apparent is that the actual waveform coming out of the DAC is the ideal waveform plus some error which you can call a glitch, correct? Okay. Now if the DAC was a perfectly linear system, in other words, if you are able to relate the output waveform to the input sequence through a linear system, okay, whether you go from 7, the code goes from 7 to 8 or from 2 to 3, the size of the step and the nature of the change in the waveform must remain the same, correct. What do you see here now? They are very different, simply because when you go from 2 to 3, I mean you get the ideal step plus, which is just delayed by a little bit, but when you go from 7 to 8, you see that there is a big spike, right, even though the change in the input code remains the same. It was the change in the code was 1 in both cases, however the change in the output waveform was very different depending on what code was there before you increased it by 1, alright. So, and please note that this is even with all elements being matched perfectly, alright. If you look at only the settled waveform, there is no difference, alright, but a lot of times we are interested in not just the settled waveform, but in the spectrum of the DAC output. Can you tell me a case in point where you have seen where you think the spectrum is important and not just the settled value? I mean you have seen this throughout this course. In a continuous time delta sigma modulator, for instance, you are not looking at the simply the settled waveform, correct, because the modulator is integrating the difference between or filtering the difference between the input signal waveform and the DAC feedback waveform, not just the settled value of the DAC, understand. And there are a lot of other situations in practice where it is not just the settled waveform of the DAC that matters, but the entire waveform, in which case this is clearly a manifestation of nonlinearity, alright. This is called dynamic nonlinearity, simply because as far as settled values or static values are concerned, everything seems fine because we assume perfect matching, alright. So, a binary weighted DAC has significant dynamic nonlinearity, since equal changes in the input code result in different changes in the output waveform depending on the initial value of the code, right, and this is all that is needed to establish the fact that a binary weighted DAC can be terribly nonlinear, especially when these glitches become, I mean clearly if this glitch is infinitely thin, then presumably it causes no effect on the output waveform, but as this glitch becomes a bigger and bigger portion of the switching period, this becomes an issue. Is this clear? Now the question is, how does a thermometer DAC respond to changes in the input code? So let me take the same 4-bit example. Alright. So, this is the thermometer code, there are 15 conductances. Okay. And whenever the code changes, what is happening? If you want to change the step by 1, you are going to add one more element. So, for instance, if the code changes by 1, the output waveform will probably do something like this, right, where I have simply drawn some glitch in the waveform, correct. That depends on details of timing skew and all this other stuff which we will not get into here, right, but this is what you will see if the input code changes by 1. Now, if the input code changes by 2, what do you think will happen? You will see a height which is double, right, and the glitch will also be twice the height. All right. Understand. So, all right. So, in other words, the glitch scales by 2x. So, in general, dynamic performance of a thermometer decoded DAC much better than that of a binary DAC, which therefore means that all things being the same, you would prefer to increase the levels of segmentation, right. And please note that this discussion had nothing to do with mismatch in the unit elements, right. So, when mismatch is also taken into account, we see that the sigma DNL also falls down if you increase the degree of segmentation, right. So, all things being equal, increased segmentation leads to better performance. Does it make sense? Right. So, the discussion so far with respect to binary versus thermometer and levels of segmentation, etc., hold for all DACs. I mean, in other words, this is not restricted to any particular kind of DAC. As an illustration, I just used conductances in parallel to illustrate the principles. Now, it is not necessary to have conductances in parallel to realize a DAC. You could also have capacitors in parallel, right, where the quantity of interest is now charge, okay, or currents in parallel. I mean, please note that what the op amp was doing here was converting, is providing this virtual ground, it is sensing the current pass through that passes through each of these conductances and converts them into a voltage, alright. So, instead of doing this, one can say, hey, how about I have current sources themselves which I can turn off and on, you understand. So, and the output, if you have current sources which can be turned off and on depending on a digital code or a digital signal, it therefore means that one can get an output which is a current, and if necessary convert this current into a voltage by passing this current through a resistor, okay. Current to voltage conversion, at least on paper, seems like a linear process, because you have a current, you pass it through a resistor and the voltage is I times R. If this I depends on a digital code, then you are all set. Is this clear? Okay. Now, this family of DACs are called current steering DACs and form a very important class of DACs used in practice, alright. And the reason why they are used so frequently is that they have very good high speed performance. I mean, the considerations of matching etc. will remain the same. In the earlier examples, the conductances had to match properly, otherwise Vref times G would change, changing the step size. In this case, the unit elements are current sources and the current sources must match properly, otherwise they will be DNL and INL just like in the other case. However, it turns out that especially at high speeds, it becomes very easy to make current steering DACs work, which cannot be said for DACs like this, okay. The reason being that A, you now need an op amp which runs at very high speed in the resistive case, and not only that, there is some feedback factor around the op amp which will also reduce the loop gain and therefore the unity gain bandwidth. And to add to all these woes, you never get conductances which are just pure conductances, nor do you get switches which are pure switches which become purely open. So, what you will have in practice is that each of these conductances will have some distributed capacitance in parallel, right, and each of these switches will have some capacitance between their input and output. In other words, when you turn off the switch, you will find that these capacitances prevent a pure open circuit. Similarly, when you turn on the switch, this capacitance which you can think of as small capacitances connected throughout the resistor. You can think of breaking this up into many small resistors in series and a capacitance from each of those nodes to ground. So, the moment you turn the switch on, it is not as if these capacitors which are all charged to Vref before, if the switch is open, right, all these tiny capacitors along this conductance will have been charged to Vref. Now, when you suddenly close the switch, these capacitors are supposed to, this potential is supposed to go to ground. So, the capacitors voltages which were all Vref before must correspondingly go down to some other values depending on their position along this resistor, right. That obviously cannot happen instantaneously, which means that there is speed limitation to how quickly you can make the output of the waveform, or rather make the output waveform switch, alright. On the other hand, it turns out that when you have a current and you want to steer it one way or the other, it can be done with very high speed, and therefore current steering DACs will become, in fact I would say, the de facto choice when you want to realize a high speed, high resolution DAC, alright. Now the basic idea is to have a unit element which can be turned on or off, alright, and you have seen an example of this already. If I draw your attention to the differential pair, let us call this D and D bar, and this is connected, the drains are connected to sufficiently high potential so that both transistors M1 and M2 are operating in saturation, right. If D bar is 0 and D is 1, when I say 0 and 1 I mean logical zeros and logical ones, then the voltage across this differential pair, this is much higher than this, which means that all the current flows through M1, okay. So and no current flows through M2. When the sign of D is changed, the opposite happens, okay. So if you think of this going in to a resistor, let us say this is VDD, alright, VOM and VOP. So VOM is nothing but VDD minus I times R times D, and VOP is nothing but VDD minus IR times 1 minus D. So the differential output voltage VOP minus VOM is pardon
2IRD
2IRD minus IR into 2D minus 1, right. So this will take on either values of plus 1 or minus 1 depending on sign of D. So the output voltage is either plus or minus I times R. Okay. The reason why this is called a current steering network is because this tail current I is either steered to the left or to the right depending on the sine of t. So, couple of things I would like to bring to your attention. One, does D have to be a full rail signal in order for us to be able to steer the tail current completely one side? In other words, should D be VDD and D bar be connected to 0 in order for this current to move completely to one side? Okay. So, let us see. Let us call this VCM plus VD VCM minus VD. As we go on increasing VD, more and more current will flow through M1. Finally, for a critical value of VD, all this current will flow through M1 and no current will flow through M2, in which case at that time what will be the potential drop here? This potential drop will simply be Vt, okay, and what will this potential drop be? Yeah, it will be VGS. What is VGS? This current flowing through transistor M1 is I. So, this voltage should be Vt plus square root of 2I by mu n Cox W by L. Alright. So, the difference between these two therefore is 2 Vd must be equal to root of 2I by mu n Cox W by L. Alright. If delta V denotes the overdrive of M1 and M2, when both of them are at the balanced state, delta V is simply square root of I by mu n Cox W by L, correct. So, in terms of this, Vd must be therefore, or 2 Vd must be root 2 times the overdrive of M1 comma M2, alright. So, this is all the voltage that is needed technically to steer the current completely one way or the other. In practice, you will have a little more than this just for safety, right, but in other words there is no real need to go full rail. Okay, in fact, you can see later on that having full rail signals is actually harmful because it causes weird things to happen at the source coupled node. Alright. Now, given this, so the moral of the story is that switching signals need not be full rail. Now, the question is how one would make the tail current source okay. So, how do you make the tail current source? Okay, version 0 would be to say, okay, I am going to have a current mirror here, and this is my switch or the current switch or the current steering pair which steers current. This is I, this is nominally supposed to be equal to I. What will happen in practice? No, forget about mismatch. Is there a systematic problem? What current will be there here? VDSs are not the same, so there will be some error. Okay, the error will be proportional to the difference between the drain source voltages of M1 and M2, and of course also the lambda of the transistor, correct. But this happens to all current sources. If you want to have a 10-bit thermometer decoded DAC, what should you do?
Copies of
Pardon? Yeah, you put 1024 of these current sources and drive each one of these differential pairs with the output of a thermometer decoder, right, where each line of the thermometer decoder is derived from the binary data and some combinational logic. Does it make sense? Okay. So, the change in the current I hat due to finite VDS is something which happens to all current sources. So, as far as the DAC is concerned, it just shows up as a gain error, right. Okay. More importantly, if there is finite GDS, so that the incremental equivalent is something like this, is there a more serious problem? Pardon? Please note that these outputs, and let us assume that we are doing a thermometer DAC like this. So, we have many pairs in parallel. And the output is developed across load resistors which are connected like this. Correct?
That means they are in linear region and they are on. That means
okay.
So whatever, I mean, depending on whether D is on or D bar is on, the voltage across that tail current source will change.
And why is that?
That is because when D is on, the positive terminal voltage will come straight away because it is in the linear region, right?
Okay, this is VOP, let us call this VOM and let us call this VOP, alright.
Okay, when D is high, you will have VOM.
Okay.
And if D bar is 1, you will have VOP.
Okay.
And different sets of current sources, depending on their individual states,
Correct.
they will have different.
That's right. So, the observation is that if D and D bar are logical levels where the voltages are so high to cause these transistors, the switch transistors, to go into the triode region, then VOP and VOM directly come across the tail current source, which means that those current sources which are connected to VOP, correct, will be slightly different from those current sources which are connected to VOM. Is this clear? Okay. Let us say the digital code is M, all right. Which means that out of a possible 2 to the n current sources, m will be having their outputs connected to so let us say this is a logical 1, the logical 0, and then you have m sources like this and 2 to the n minus m sources, where this is connected to 0, this is connected to 1, all right. If these devices are in triode, which is what will happen when these gate potentials are pushed too high and low, or if the supply voltage is not sufficiently large, okay, then clearly this potential will be what? VO m, correct, because this switch is on. On the other hand, this potential will be VO p, all right. So, this actual current will be m times I plus VOM by actually it is not simply VOM by RDS, it will be VOM minus some VGS, right. I mean, if you assume that all these are coming from a master current source, right, it is actually VOM minus VGS divided by or multiplied by GDS. Correct. So, if VOM is the same as I mean VGS, you have I, but the key point is to note that you have VOM here. And similarly, what is the other current? 2 to the n minus m times I plus VOP minus VGS times GDS, and therefore, the difference in the output voltage, this is VO m, this is VOP. So, VOP minus VOM is therefore equal to 2 to the n minus m times 2 to the n minus 2m times I plus VOP times 2 to the n minus m minus times GDS minus VOP times m times GDS, okay, plus m times VGS times GDS minus 2 to the n minus m times, or I just club these two terms, it will be m minus two to the n. So, the m goes away, it does not go away, right, it is 2m minus 2 to the n times VGS times GDS. This is right. It seems okay. Into, oh sorry, into the output resistance R. All right. So, what do you, I mean, without getting into major computation, what can you say about this relationship? What do you want finally? If GDS is 0, which means the output impedance of every current source is infinite, how is VOP minus VOM related to M? Yeah, which is, it is basically a, I mean, if you forget about the offset 2 to the n times I, right, this is a linear relationship in M. I mean, here M must go from, when 0, it goes from 0 to 2 to the n, obviously there must be an offset, right, because the DC value is always positive, right. M goes from, I mean, if M went from minus, find, I mean, whatever 2 to the n minus 1 plus 2 to the n minus 1, then you can expect the average to be 0. That 2 to the n times capital I is an offset, we do not have to worry about it. What is important is to notice that if GDS was 0, VOP minus VOM is a linear function of M. The moment there is finite output impedance, what do you think will happen? This whole relationship is no longer linear, right, and not only that, it turns out that this GDS will also depend on VOP and VOM. So, this is first of all vastly simplified, and to make things worse, GDS is also dependent on VOP and VOM. So, basically if the current sources start depending on the output voltage, it will mean, I mean, through the, which will happen through their finite GDS, it means that the DAC will become nonlinear. Okay, in the next class we will do a more careful computation of the DNL and INL that one can expect when you have finite output impedance. One other point that I wish to make is that it does not have to, these transistors do not have to be in the triode region for that to happen, right. If these transistors are in saturation also, there will be a component of that voltage which will be dependent on, I hope this is clear to you. Right. So, if let us say this is VB1, VB2, alright. Even if M2 and M1 are both in saturation, right, if this changes by delta V, or if this is yanked up by delta V, what happens to this node? This will go up approximately by delta V by GMRO of which transistor? Of M2, okay, right. So, even if the transistor, the switch transistors are in the saturation region, that tail node will have components which are depend on VOP and VON. So, you get only a respite of a factor of GM times RO, okay. So, the next class we will get into this in more detail.